In the remote and economically challenged region of West Papua New Guinea, an e-waste dilemma unfolds alongside significant poverty, limited healthcare access, and financial constraints. This multifaceted issue stems from discarded electronic devices such as smartphones and laptops taking an unpredictable path due to the absence of proper e-waste management infrastructure. The result is not just environmental threats, but also the endangerment of local communities' health and well-being due to the hazardous materials within the e-waste. Moreover, informal recycling practices, while well-intentioned, inadvertently expose individuals to harmful substances.
Addressing this challenge requires a dynamic approach involving heightened awareness and community education, made more complex by the region's isolation, rugged terrain, and limited resources. Collaborative efforts among government agencies, non-governmental organizations, and local communities are essential to build robust e-waste management infrastructure, promote responsible recycling, and mitigate the e-waste problem. Recognizing the intersection of e-waste issues with poverty, healthcare disparities, and financial limitations underscores the need for comprehensive strategies. It's a journey filled with awareness, action, and transformation, one that begins with each of us and holds the promise of lasting change.
In today's tech-savvy world, we're surrounded by electronic devices from smartphones to laptops that have revolutionized how we live and work. Yet, as these devices reach the end of their life cycle, they often take on a new identity: electronic waste. This transformation raises critical environmental concerns as many electronic components contain hazardous acidic materials that can harm our environment if not managed responsibly.
The city of Surabaya, especially in the northern, western, and eastern parts, had potential for e-waste generation in 2019. Recorded in the northern parts of Surabaya, the potential amount of e-waste generated by the community is 2,421 tons per year. And as the time passes by, the results are showing that 83% of the schools generated e-waste for the IT and communication device category. Depending on the number of students and school levels, the annual e-waste generation varied from 3 to 24 units per school, or 12.25 to 115.40 kilograms per school, or 0.032 to 0.161 kilograms per student.
In our experiment, we delve into this pressing issue while introducing the concept of e-waste. We aim to demonstrate a practical and eco-friendly solution using a readily available household item, which is baking soda. Through this experiment, we'll unveil how baking soda can effectively neutralize the harmful acids present in e-waste, offering a simple yet impactful method for safer disposal. By engaging in this hands-on experience, we not only gain deeper understanding of the challenge posed by e-waste, but also equip ourselves with the knowledge to contribute to a more sustainable and environmentally conscious future. This experiment bridges the gap between technology and environmental responsibility, inviting us to be mindful stewards of our planet.
Okay, now that Elana has given us a brief introduction about our research experiment, we are going to be diving deeper into it and talk about the specifications and the procedures. So starting off with the hypothesis, which is basically that the baking soda is a base, and when it is added to the e-waste samples, which contains acidic elements to it, the baking soda neutralizes the e-waste, and the contact of these two creates a fizz. And when this fizzing stops eventually, it indicates that the e-waste sample has been completely neutralized.
The aim of this experiment is to demonstrate how baking soda can be used to neutralize the harmful effects of acidic e-waste components in a safe and eco-friendly manner.
The materials needed for this experiment are an old phone and a keyboard to get 4 copper sheets and 4 circuit board samples. Number 2, 25 grams of baking soda. Number 3, 50 milliliters of vinegar. Number 4, 2 small containers or cups. Number 5, safety equipment that includes gloves and safety goggles. And lastly, litmus paper.
Once you have the materials, we can start by making sure to put on safety gloves and safety goggles to protect yourself when breaking the phone and keyboard needed for the sample. Next, prepare the small piece of e-waste like the broken circuit board and copper sheet, then place it in the beaker. You can pour 50 milliliters of vinegar into the other container or beaker. As vinegar is a mild acid, you can easily find it in households. Then carefully observe what happens when you pour vinegar onto the e-waste sample. You may notice fizzing or bubbling like this, which indicates a chemical reaction. Then sprinkle 25 grams of baking soda onto the e-waste sample that has been exposed to vinegar. As baking soda is a base, it can neutralize acids. After a few minutes, observe how the baking soda reacts with the vinegar-treated e-waste. You should see that the fizzing and bubbling decrease or stop, indicating that the acid from the e-waste has been neutralized.
Okay, so now continuing with the procedure, here's the seventh one, in which we used 4 samples with 2 different batches with different time variables, in which in the 24-hour sample we used 2 circuit board samples and 2 copper sheet samples, and the same thing for the 48-hour, but just in a different batch, and then observed the changes. For the 8th one, we need pH indicating strips and litmus paper, in which first we measured the pH of vinegar before using the pH indicating strips, and as we can see here, we got a pH of 2, and then after the neutralization happened, we rechecked the pH, and in the 24-hour sample, as you can see, we got a pH of about 6 to 7, and in the 48-hour sample, we got a pH of about 8 to 9. Now here you can see all of our 8 samples in which we dipped in red litmus paper, which turned into purple, indicating neutralization happening. So now we're going to be talking about the analysis that we did, in which we observed the reduction in fizzing as the time was increasing after adding the baking soda, which was an eco-friendly e-waste management solute. And after in the 24-hour sample, we could still find a few bubbles remaining, indicating that it wasn't fully neutralized. But in the 48-hour sample, we could not spot any bubbles there, indicating a more neutralization or a higher pH in it.
As we have understood from this experiment, we can conclude that the longer the e-waste containing acidic elements stays in the baking soda solution, which is a base and also known as the eco-friendly solution, the higher the pH level it has and becomes more neutralized.